What happened to start inflation off? The answer is we don't know. When did inflation start?
The early universe was cold instead of hot. That is not going to happen. That's not how science works.
Now, our remote future then, because there's nothing left with any mass, becomes equivalent.
Galaxies draw together. Matter grows denser. The universe becomes smaller, hotter, and brighter. Keep rewinding, past the first galaxies and the first stars, and eventually we reach a time before atoms could exist. Space was filled with glowing plasma. Light could not travel freely. Then, about 380,000 years after the hot Big Bang, the plasma cooled enough for atoms to form. Light escaped. Stretched by cosmic expansion, that ancient glow surrounds us today as the cosmic microwave background, the oldest light we can see. But even this is not the beginning. The microwave sky is a photograph taken after the decisive events were already over. Its tiny variations carry clues to an earlier, stranger epoch, perhaps inflation, and to the limits of everything our tested theories can describe. So what happens if we keep going backwards? What was there before the Big Bang? Look closely at the microwave sky and it is not smooth. The warmer and cooler regions trace tiny differences in density. Over billions of years, gravity amplified those differences. Slightly denser regions gathered more matter, matter-formed filaments, clusters, galaxies, stars, planets, and eventually observers able to map the pattern. In that sense, the CMB is both an ending and a beginning, the last light trapped in the primordial plasma, and the blueprint for the structure that followed. We can test this connection. The statistical pattern in the CMB agrees with the large-scale distribution of galaxies. Ripples in the early plasma left a preferred scale, now measured as baryon acoustic oscillations across the cosmic web. This is the evidential strength of modern cosmology. We do not merely run a film backwards because it feels plausible. Independent observations converge on the same expanding history. But every measurement has a horizon. Electromagnetic telescopes cannot look through the opaque plasma directly. Earlier events must be reconstructed from consequences they left behind. That distinction matters. The CMB is observed. The hot plasma is strongly supported by physics and multiple measurements. As we move closer to the earliest moments, inference becomes more dependent on energies no laboratory can reproduce. The map remains our anchor, but the certainty begins to change. Rewind the expansion and ordinary distances shrink. Matter becomes denser. Radiation becomes hotter. Galaxies dissolve into gas, atoms are ionized into plasma. Continue backwards and even nuclei cannot remain assembled. During the first few minutes, temperatures fell through the range where protons and neutrons could combine. The result was primordial nucleosynthesis, mostly hydrogen, a great deal of helium, and traces of deuterium and lithium. Astronomers measure those abundances in ancient gas, and the broad agreement with nuclear calculations is another independent test of the hot early universe. Earlier still, within the first second, the cosmos was a rapidly changing particle environment. Neutrinos stopped interacting efficiently with matter. Protons and neutrons exchanged identities until expansion and cooling froze their relative numbers. We cannot photograph these moments, but their physics leaves measurable relics. This is what the hot Big Bang model describes, the evolution of a universe that was once much hotter and denser than it is today. It does not, by itself, tell us that everything exploded from one point into pre-existing emptiness. Every sufficiently distant region is receding because space itself is expanding on large scales. There is no measured central blast site and no known outer edge into which debris is flying. The familiar explosion picture is vivid, simple, and misleading.
So here's the point. The tenets of the Big Bang, that the universe started out small, hot, dense, where matter and energy were a primordial soup, where the forces of nature had merged. All of that is thoroughly supported by observations of this universe. Thoroughly supported. Okay? Now, there's some things that, well, did this really cause that? Or might it be something that we don't know about yet? And who ordered up the dark matter? We don't know where that came from. And where's this expansion? We don't know where that came from. But we can describe it, and we can measure it. Here's the point. If tomorrow you have a new idea...
The phrase Big Bang carries several meanings. Sometimes it names the whole expanding cosmological history. Sometimes it means the hot, dense phase whose relics include the microwave background and primordial elements. And sometimes it is used for a hypothetical absolute beginning. Those are not the same claim. The evidence for a hot early phase is powerful. The claim that known equations describe an absolute first instant is not. General relativity lets us extrapolate an expanding universe backwards. Under broad conditions, that extrapolation reaches a boundary where density and curvature diverge, a singularity. But a singularity is not a photographed object or a physical mechanism. It is often a warning that a theory has been pushed outside its domain. General relativity does not include a quantum description of space-time. At sufficiently extreme scales, leaving quantum physics out is unlikely to be justified. So the classical equations may tell us that their own account becomes incomplete, not that they have revealed a literal point from which all existence emerged. This is why careful cosmologists separate the hot Big Bang from the deeper origin question. The hot phase is part of our best supported history. What prepared its initial conditions remains open. And one influential proposal changes the sequence dramatically. Perhaps the hot Big Bang was preceded by an episode of accelerated expansion called inflation. Inflation was proposed to explain features that otherwise look surprisingly coordinated. The observable universe is extremely uniform on large scales, even though widely separated regions appear too distant to have exchanged light in a simple non-inflating history. Spatial geometry is also very close to flat. Inflation proposes that a tiny region underwent a brief period of accelerated expansion. Regions that were once close enough to interact were driven far apart, while any initial curvature was stretched toward apparent flatness. This is not an ordinary explosion of matter through space. It is a change in the scale of space described by a field with unusual energy properties. When accelerated expansion ended, energy associated with that field could be converted into a hot bath of particles and radiation. On this account, the hot Big Bang is not necessarily the ultimate beginning. It is the hot aftermath of inflation. That shift is scientifically important and linguistically awkward. People may call inflation part of the Big Bang, or say it happened before the Big Bang, depending on which definition they use. Brian Cox makes that distinction explicit. If the Big Bang means the hot dense phase, a preceding inflationary era belongs in the textbook picture. But inflation is a framework, not a single complete model. We do not know the identity of the inflating field, what set it in motion, or exactly how it ended. Inflation has an extraordinary consequence. Quantum fluctuations, microscopic and unavoidable, would have been stretched to astronomical scales. Slight variations in the inflationary field became differences in density. Those differences later shaped the CMB and the cosmic web. Several broad predictions fit observation. Fluctuations are nearly scale invariant, close to Gaussian, and predominantly adiabatic. That agreement is why inflation is taken seriously. But agreement with a family of predictions is not the same as identifying one verified mechanism. Many inflationary models can reproduce current data. Some versions continue eternally in distant regions, producing a much larger structure beyond our observable patch. Others do not. Primordial gravitational waves could provide a powerful clue. A distinctive curl pattern in CMB polarization might reveal the energy scale of inflation, but no confirmed primordial signal has yet selected a model. Dust in our own galaxy can imitate part of the signature, so claims require severe scrutiny. The honest status is mixed. Inflation offers a compelling explanation for several observed features, and its predictions have scored real successes. The underlying physics remains theoretical. And even if inflation happened, the question merely retreats. What established the conditions for inflation? Was there an earlier phase? Did inflation have a beginning? Or is the request for an earlier cause already assuming a kind of time that did not yet exist? In everyday language, before is harmless. One event occurs, a clock advances, another event follows. But relativity does not treat time as a universal river flowing outside the universe. Time is part of spacetime, linked with geometry, matter, and energy. Clocks measure paths through that geometry. Near black holes, in an expanding cosmos, or for observers in relative motion, durations need not agree in the simple Newtonian way. Push general relativity toward the early universe and the geometry itself becomes dynamical at extreme curvature. Then ask what happened before spacetime had the structure required to define ordinary clocks. The grammar survives, but the physical meaning may not. A familiar analogy asks what lies north of the North Pole. The question uses a valid direction beyond the point where that direction is defined. The analogy is imperfect. Cosmological time is not literally latitude, and viable models can extend through an early boundary. But it exposes the assumption hidden in the word before. We picture a blank temporal stage waiting for the universe to appear. Physics has not established such a stage. Nor has it established that there was nothing. The correct conclusion is narrower. Ordinary temporal intuition cannot decide the issue. To investigate the earliest regime, we need a theory in which gravity and quantum mechanics are both present. Without quantum gravity, classical extrapolation is an unfinished calculation presented as an origin story.
Because it really does seem to be giving us a glimpse of a deeper theory of gravity. The simple way to say it seems that space and time are not fundamental. So one view, and I emphasize that there are other views, we're at the cutting edge of research now, but one view is a field which has become known as emergent space-time.
Quantum mechanics describes particles and fields with probabilities, superpositions, and uncertainty. General relativity describes gravity as curved space-time. Each is astonishingly successful in its tested domain. Near the classical beginning, both should matter at once. Yet there is no experimentally confirmed, complete theory of quantum gravity. Candidate approaches include string theory, loop quantum gravity, causal sets, and other programs. They do not currently deliver one universally accepted cosmological prehistory. This gap changes what a responsible answer sounds like. We can calculate backwards through nucleosynthesis with confidence. We can infer conditions around recombination with precision. We can test broad properties associated with inflation. But at roughly the Planck scale, our familiar separation between matter evolving and spacetime providing the arena may fail. Some mathematical descriptions replace a sharp beginning with a quantum transition. Some make time emerge from more fundamental relations. Some retain a meaningful earlier phase. These proposals are not interchangeable, and none has been decisively confirmed. Neil deGrasse Tyson often frames the frontier as a hierarchy of models. The hot Big Bang explains a major body of evidence, while the deeper theory that contains it remains unknown. A future theory would not have to discard the successful hot Big Bang, just as relativity did not make Newtonian mechanics useless. It would explain why the older description works, and where its question about before stops being complete.
Well, what's the Big
I get
Bang?
a C+ on that one.
Yeah, it's what came before the Big Bang. We call it the Big Bang.
The Big Thang. Okay, that's a B+. If that's what's your thing? Yeah, that's before the Big Bang.
Yeah, it was before the Big Bang.
One class of ideas takes the boundary seriously. Perhaps cosmic time has a finite extent into the past, without requiring an earlier moment. This need not mean the universe popped from philosophical nothingness. It may mean that the geometry has no past-directed extension of the ordinary kind. In quantum cosmology, the wave function of the universe can be described over possible geometries rather than as matter moving on one fixed background. The Hartle-Hawking no-boundary proposal is a famous example. Near what classical language calls the beginning, the mathematical roll of time becomes more like a spatial direction. A smooth geometry can close off without an edge, somewhat as Earth's surface closes at a pole without a boundary line. Farther from that regime, ordinary time emerges and the universe expands. This is a theoretical construction, not an observed account of creation. Its predictions and even its most appropriate mathematical formulation remain debated. But it shows why know before need not be equivalent to a blank eternity followed by a sudden event. The concept of an earlier instant might simply not apply. Other beginning of time models reach similar verbal conclusions by different mathematics. Their challenge is to connect an elegant boundary condition to distinctive observations. Without that bridge, conceptual possibility is not empirical knowledge. The idea earns a place in the documentary because it clarifies the question, not because science has verified that time began in exactly this way. A beginning without a prior moment confronts another intuition: everything must have a cause. Causation, however, is normally defined through temporal order. A cause precedes an effect, or at least participates in a space-time relation. If ordinary time is emergent, demanding a preceding cause may import the very structure the model says is absent. That does not prove the model. It only prevents common sense from settling the physics by decree. Cosmologists instead ask operational questions. Does the proposal produce a universe that can become large, structured and approximately classical? Does it yield a plausible spectrum of primordial fluctuations? Can it assign probabilities consistently? Could another model make a different measurable prediction? These standards turn metaphysical-sounding language back into science. They also reveal how little is established. We do not observe a no-boundary transition. We observe a late surface of light and infer earlier conditions through a chain of tested theories. Near the foundation, different assumptions can generate similar later universes. This is a problem of lost information as well as high energy. Inflation itself may erase traces of what preceded it by stretching earlier structure far beyond the observable horizon. If so, the universe may contain a physical history that present observations cannot recover. But May is doing essential work. An observational limit is not evidence for one preferred answer. It is a reason to keep certainty proportional to what the sky actually tells us. Other models preserve a meaningful earlier phase. In a bounce scenario, a contracting cosmos reaches an extreme but finite density and transitions into expansion. Quantum geometry, exotic matter, modified gravity or extra dimensions may provide the mechanism, depending on the model. The classical singularity is replaced by a bridge. A bounce is not automatically cyclic. There may have been only one contraction. And a cyclic universe is not automatically the old picture of expansion followed by a simple gravitational collapse. Modern cyclic proposals are diverse. Some pass through repeated brane interactions. Some use quantum effects to reverse contraction. Each must control instabilities, explain entropy, and reproduce the measured primordial spectrum. These are hard requirements, not decorative details. A contracting phase can transform quantum fluctuations into large-scale structure, offering an alternative to inflation in some models. It can also generate distinctive non-Gaussian patterns or gravitational wave spectra. That creates a possible route to testing. But no bounce signature has been confirmed. The attraction is clear: an earlier cosmos gives the word before a physical referent and avoids an absolute classical beginning. The cost is new physics in a regime we cannot directly access. A viable model must do more than remove a singularity from an equation. It must connect the transition to the remarkably specific universe recorded in the CMB. Until then, bounce cosmologies remain serious theoretical research, not evidence that our cosmos definitely had a previous life. Roger Penrose proposes a different kind of cycle, conformal cyclic cosmology. Our universe, in this picture, is one eon in an unending sequence. Each eon begins in a hot Big Bang and expands for an immense time. In the remote future, stars die, black holes evaporate, and the cosmos becomes dominated by radiation. Penrose argues that when meaningful mass scales disappear, the infinitely expanded future can be conformally related to the Big Bang of a new eon. Conformal geometry preserves angles and causal structure while discarding absolute scale. The enormous old universe and the tiny young one can then be two descriptions joined across a boundary. It is a bold mathematical idea. It does not resemble a universe mechanically shrinking and exploding again. Penrose has argued that violent events in the previous eon might leave circular features or Hawking points in our microwave background. He and collaborators report candidates. Other cosmologists dispute the statistical interpretation and do not regard the evidence as established. That disagreement must remain visible. Conformal cyclic cosmology is valuable here because it turns before into a concrete, potentially testable claim. A previous cosmic eon may have left traces. But the traces have not convinced the field. The proposal is speculative relative to the standard hot Big Bang history. Its proper role is not to deliver a twist ending. It is to show what a competing answer must eventually do, risk being ruled out by data.
Why did you change your mind? See, because I used to believe the Big Bang was the beginning, and now I'm saying, no, it's not the beginning. I had these theorems with Stephen Hawking, these theorems about singularities, and they could say in very general circumstances, if you believe Einstein's theory, you've got to run in this singular state where things go wrong. So that's the beginning. So, well, you have to have your way around that. And I thought the reasons against it against it just being the beginning, were much stronger than the previous reasons I had for believing in it. So, yes, changing your mind is part. I think I said in the interview, well, I think being a scientist, I'm allowed to change my mind if the evidence starts to point the other way.
Very true. I mean, you did.
Theories of a prehistory face a profound filter. Whatever happened earlier must survive into quantities we can measure now. Inflation may dilute earlier features. A bounce may process them. A conformal crossover may transmit only particular scale-free effects. The later hot plasma then scatters light until recombination, hiding direct electromagnetic views. This is why the CMB appears again and again. It is not the Big Bang itself, it is the earliest transparent screen onto which earlier physics might have projected a pattern. The same map can test rival stories, but interpretation is difficult. Our galaxy adds foreground radiation. Instruments add noise and systematics. A posteriori searches can find patterns that look impressive after the question has been chosen. Robust evidence requires predictions stated in advance, independent datasets, and statistical methods that account for all the places a signal could have appeared. Scientific caution can sound less cinematic than certainty, but it is the engine of progress. Penrose himself changed his view that the Big Bang must be the beginning. Brian Cox distinguishes inflation from the hot Big Bang while emphasizing what remains unknown. Neil deGrasse Tyson stresses that evidence determines which ideas survive. These are not three celebrity answers to a poll. Together they expose the structure of the problem. Definitions matter, theories extend successful evidence, and every extension owes the sky a test. The next clues may come from several directions. CMB experiments continue to measure polarization with increasing sensitivity. A primordial gravitational wave background could reveal physics at energies far beyond particle accelerators and help distinguish inflationary models. Its absence over a wider range would also eliminate possibilities. Large-scale structure surveys map millions of galaxies, measuring how primordial fluctuations grew under gravity. Baryon acoustic oscillations preserve a standard scale from the early plasma. Weak gravitational lensing traces invisible matter. Together these datasets test whether one consistent history connects the microwave sky to the modern cosmic web. SPHERX surveys the whole sky in many infrared colors, studying the distribution of galaxies and seeking signatures related to inflation through large-scale clustering. Euclid, Roman, and ground-based surveys add complementary precision. Gravitational wave observatories may eventually reach backgrounds produced by phase transitions, cosmic strings, or a bounce. No single mission is a machine for seeing before the Big Bang. Each measures a consequence predicted by some models and not others. The scientific target is discrimination. A theory gains force when it makes a risky quantitative prediction that survives measurement. It loses force when its distinctive signal is absent or when another model explains the same data more simply. The boundary of knowledge can move, but only if speculation is translated into observables.
It seems that there is a deeper theory underlying what we think of as space and time, which is a quantum theory. And so the idea is that space and time themselves emerge from what? From quantum entanglement, from some kind of smaller parts or pieces. We don't know what those things are. We don't know the nature of them. But it does seem that there's a deeper underlying theory from which space and time emerge. That is what we call the quantum theory of gravity.
There may also be fundamental limits. We observe only a finite region because light has traveled for a finite cosmic time. Inflation can place relevant scales beyond that horizon. Quantum processes may allow only probabilistic statements. Different early histories may converge on nearly identical later conditions, erasing the evidence needed to choose between them. Science is not guaranteed an answer to every grammatically valid question. But ignorance today is not proof of permanent unknowability. The cosmic microwave background was once undetected. Gravitational waves were a mathematical prediction for a century before instruments measured them directly. Primordial element abundances became precision tests only when nuclear physics and astronomical spectroscopy matured. New windows can turn philosophy into measurement. The discipline is to say exactly where that has happened and where it has not. We know the universe is expanding. We observe the CMB and early galaxies. We strongly support a hot dense past and primordial nucleosynthesis. Inflation is a leading theoretical framework with successful broad predictions but unresolved microphysics. No boundary, bounce and cyclic accounts are theoretical or speculative, with no confirmed observation selecting one. Those categories do not insult the ideas. They describe their current relationship to evidence. The answer to what was there before the Big Bang may depend on a future detection, a deeper theory of time, or a demonstration that the question has no unique observable answer. Return to the oldest light. Across the sky, its minute variations preserve a history stretching from a hot plasma to galaxies and observers. Physics can reconstruct that history with a precision that would have seemed impossible a century ago. We can calculate the first minutes. We can infer the first seconds. We can test patterns seeded far earlier. But the map is also a boundary. It does not show an absolute beginning, and it does not reveal one verified scene before the earliest phase our theories reliably describe. If the phrase Big Bang means the hot expanding state, inflation may have preceded it. If it means the classical boundary of space-time, quantum gravity may replace the question with something stranger, a smooth beginning with no earlier moment, a bounce from contraction, a previous eon, or a possibility not yet imagined. Present evidence does not choose one. So what was there before the Big Bang? The scientifically honest answer is not simply nothing, and it is not confidently something. It is that the word before reaches beyond established knowledge. The question remains useful because it forces definitions, exposes the limits of equations and tells future observations what to seek. The oldest light cannot answer alone. But every tiny feature in it is a message from a universe that was already in motion, and an invitation to keep reading backwards.